We can look at converting chemical energy, gunpowder, into mechanical energy to launch a cannonball and kill people. We could look at chemical energy blowing up inside a car engine to turn into mechanical to cause the car to move. We can look at chemical energy breaking a bond, allowing us to exist. So pretty much everything on this slide comes back to chemical energy. Right? So chemistry is what drives virtually all of these things. Okay? So within that, we can look at kind of a subcategory of that for kinetic energy. Okay? If somebody was to, say, study kinesiology, what are they studying? Okay? Kinesiology is, we have some kinesiologists, don't we? Do we not?
No.
Kinesiology is the energy of usually people moving. It's usually what you're studying. Because the prefix, the kin, or the kine, I don't know, K-I-N, probably with the E, is talking to movement. So when we're talking about kinetic energy, we're talking about the energy associated with things moving. All right? So what we want to do is look at our phases. So we've got 3 pictures up here representing solid, liquid, and gas. Okay? Within those, would we expect the solid to have a lot of kinetic energy? No. Why not? Why wouldn't it move?
It's too dense.
It's too compacted. Those particles don't really have a lot of space to move. If we add enough energy, we can cause them to start to move, which then changes the phase. Okay, and we get a liquid phase. If we continue to add energy, we can break all the interactions between them, and we can bust out into the gas phase. Okay, and they now have tons of motion. So what this is really kind of getting at is that we can look at the kinetic energy for each of our phases. For solids, we would expect the kinetic energy to be very low, and for gases, it should be very high. Is it 0 for solids? No. So when I look at this table, eventually I'm going to see it just start moving, right? Okay. Well, if it has kinetic energy, doesn't it have movement? It's so small that we can't see it. Each of those atoms is potentially vibrating. We just can't see that vibration. It's outside the realm of our human visibility. Okay? That said, as a rough approximation for solids, we usually say their kinetic energy is 0. Okay? So how did we transition from the solid to the liquid to the gas?
Temperature.
We added temperature. Well, if our kinetic energy increased across those phases, what happens with our temperature? Same deal. So they're proportional. Okay? As we increase temperature, we also increase kinetic energy. That's all we're trying to get out of that. Okay? Which will then move us into Chapter 8, exciting, fun stuff. Okay, so we've now recovered from everything that we should have talked about in the last unit that I didn't, and we now move into the mole concept. Okay? The next sequence of chapters is all kind of cut up all over the place because really all I'm trying to do within them is to get you to recognize that all we're doing is the same thing we learned in Chapter 2. Okay, that's it. We just repeat it a whole bunch of times. Okay, all we are doing is conversions. And you might say, well, don't I want to learn something about what those units mean? Don't I want to know what a mole means before I just start doing conversions? Okay. Well, when you were born, did you know the exact conversion between inches and centimeters? No. Did you learn what that conversion was before you started working with inches and centimeters? No. Same thing's going to happen in chemistry. We're going to express these new unit systems like moles, okay, and molarity, and molar mass. And we're going to expect you to work with them at the same time that you're learning about those concepts. The intent is not to break you because now you're trying to do too many different things. The intent is to get you working with it enough that you can start to work towards using it and processing it at the same time. Okay? That will allow you a deeper understanding than instead of just sitting here and being like, I wonder what a mole is. Okay? Kind of makes sense? Okay. You guys trust the method? Yeah? How do we do it? For an entire classroom full of people that trusted the method, I'm a little bit nervous about silence and how do we do it. Okay, we want our answer. What do we want for an answer? Okay, we want micrograms. That's that weird symbol. Now what should we do? Killing me with the silence. What do we got?
You got milligrams.
Okay. We would take our given information. In this case, we only have milligrams. Okay, so we would just throw that in, milligrams. Where do we want to place that milligram? Why do I want it on top? So I like the far left. Okay, because it's given, unfortunately, is not a good enough answer. Because if I give you something with 3 or 4 pieces of information, they're all given. Should you place all of them in the numerator? No. Okay. So let's go through that. That's where we get it in the answer. So milligram is what I have as an answer?
No.
It's what? It's mass. Milligram is a measurement of mass. Microgram is a measurement of mass. Because they're both mass units, it makes sense to place them both in the numerator. What would be in the denominator? 1. Okay. The reason being, that is all that is given. It's just that substance. Is milligram the same as microgram? So what do we do? Okay, we need to do a conversion, right? We need to get rid of milligram. Ideally, what happens? So that would cancel out milligram, yes. I want microgram. Do I know that conversion? No. Okay? The same process is going to happen with all our other conversions. We're going to go through and say, I want to get rid of one and I want to get one. Does that conversion factor exist? Yeah. If your answer is no, then you've got to convert to something else. Okay? The idea is that that something else takes you closer to where you want to get. Okay? I could convert milligram, never mind. What do I want to convert milligram to? Why you pick grams? You know that, but we could probably also look at milligrams into pounds. I don't know what it is, but we could do it. Why do we want to keep it metric? I could go milligrams to decagrams. Okay, looking at our factors of 10, recognizing that in our next sequence, what we could probably do is cancel out grams and bring in micrograms, because we're now looking at that power of 10 shift. Kind of makes sense? Now we'd have to know the numbers to place. What did milli mean? 10 to the negative 3. What does micro mean? Good. 10 to the negative 6. We can now punch in our numbers, do our calculations, we'll be done. Yeah? Straightforward, simple, and easy, right? Right. Okay? So let's take a look at something that's just kind of a side project. Okay? I apologize for the small font. You'll understand why in a second. If I asked you to convert 2,437,000 inches into miles, but only using alphabetic symbols. So, well, it's not that hard, right? You know, alphabetic symbols. Step 1, I wanted miles. And I'm starting with 2,437,000 inches. I want to get rid of inches. I want miles, right? Do I know that? No? Okay, what can I convert inches to? Feet. So I can do feet into miles. Do I know that? Some people might, some people might not. Very, very least 1 foot is 12 inches. And then what is it? 5,280 feet is 1 mile. Thank you, imperial system. Okay. Oh, we got it. Well, that wasn't that bad. That was all alphabetic letters, wasn't it? No, virtually none of that was alphabetic. Okay. If we asked you to go through and write this as alphabetic text, how long do you think it would take? So when you talk about the process being a horrible process, it sucks, it's awful, it's horrible.
Don't make that an extra.
I could make you do something else. Okay? This is what you should be thinking about and processing. So when we talk about conversions, and some people are like, oh, it's easy, I get it. You're used to dealing with those manipulations. Those people that aren't, this is likely what you are trying to process. You're processing all of that text and turning it into that simple little equation that we just drew out. Right? So if it feels daunting, it's daunting for a reason. You have to get used to that patterning to be able to establish those conversions. Kind of make sense?
Yeah.
Okay. This was a project assigned to students in a different class that I teach as a partner with an English class. And he was like, well, everybody keeps screwing up conversions. Just make them write it out. I was like, okay, we'll just do that. He's like, no, make them write it out and do that. I was like, fine. So I followed along with it and I did it. You'll notice there's a little bit in italics at the beginning of this.
Yeah.
Because you've in theory all done writing classes. When you write something out, you should start with like a thesis statement. If you ignore all of the italics, there was no thesis statement. This little Molar effort was like, you didn't include a thesis statement. You got to fix your writing. Okay, after all that other text, he was like, it's not good enough. Okay? So when we think about what we're trying to do, even in English, we're doing the same thing. We're coming up with what are we trying to do? What is our goal? What are the steps that we need to take to move through and do it? Okay? So if at some point you're struggling with how to go through and solve something, you may not like it. Write it out in alphabetic text. Okay? Write out each of those processes. Remember how I said I ask easier questions that you all answer and we work through the conversion together? Okay? What you need to be doing on the exam is asking yourself those easier questions. How many of you have been writing down my easier questions? Oh, if you haven't been writing them down, are you going to know what questions to ask yourself on the exam? No. Okay, so if you are struggling with conversions, what you might do is shift your note-taking process to, instead of writing down the answer of the whole solve, write down the questions. Okay? What questions did Mike ask to get this statement written in? Okay? Make sense? Okay. So, yeah, this works. All right, the title's a little bit off. Let's wait a second. That is not what I thought I was coming up into next. Did I skip ahead? What did I do? Huh. I don't know why that's there, but we can look at it a little bit. All right, let's look at some of the potentials with this. How many atoms of sodium are needed to make one molecule of sodium carbonate? Actually, it does work. What is sodium carbonate? Sodium is Na, carbonate is CO3. How do we know that? Yeah, fair enough. You're right. You memorized that. Okay. You are required to memorize that carbonate is CO3. You are required to memorize that sodium is Na. Is that a correct formula? Why? It's not balanced. So what else do we have to check? Charges. What's the charge on sodium? +1. The charge on carbonate? How do we know that?
Memorized.
Okay. How do we fix our formula? Na2CO3. Okay. We had the alphabetic text. Alphabetic text is confusing. So what do? We rewrite it. So now the question was, how many atoms of sodium are needed to make one molecule of sodium carbonate? 2. How'd you do that? Well, you're going like, it's obvious, dude. It's not obvious if you can't explain it to me.
This would be 2 sodiums to make sodium carbonate.
Okay. What does one sodium carbonate molecule look like? Yeah, that's it. It's what's in the box. That is one molecule, molecules, of course, molecule of our sodium carbonate. How many sodiums are in that box?
2.
How do you know that?
Notation.
That subscript 2 applies to what's directly in front of it. There it is. What did we just write? We just wrote a conversion factor. Which means what could I now potentially do? Conversions. Yay! Where did I get that conversion factor from? How did I determine the conversion factor that one molecule of sodium carbonate was 2 atoms of sodium? Where did I get that from?
The equations.
Did I get it from the equation? No, I didn't get it from an equation. What did I get it from? The chemical formula. Okay? Chemical formulas have lots of embedded information in them. Okay? So we could pull that out. Okay? How many molecules of sodium carbonate are needed to make 2 molecules of sodium hydrogen carbonate? Oof, that's a lot of text. Okay? So sodium hydrogen carbonate, that would be, I believe, NaHCO3. And how many of those molecules did I want? 2. How many molecules of sodium carbonate? Well, sodium carbonate, I believe, would be Na2CO3. What does that chemical equation tell me? I need 1 sodium carbonate to make 2 sodium hydrogen carbonate. What did I just write? Or what will I now write? I now have a conversion factor. Okay? I'm a little bit bummed that I just erased all that other work I had up there. Okay? Why am I bummed? Because guess what we just wrote in that previous work? What was that previous work? I said 2 sodium equals 2, what was it, molecules of sodium? I know, I'll fix the 2 in a second. 1, right?
Yeah.
Atoms of sodium, right? Guess what the purple text is? A conversion factor. It is also chapter 8. Guess what the black text is? Conversion factor, that is chapter 9. Yeah, I fixed 1, 2 to goof it. All right. All of chapter 8 is focusing on how do we use chemical formulas. Do you know how to use chemical formulas? Did you get this conversion factor? Yeah. So do you know how to use chemical formulas?
Yeah.
Cool, you know chapter 8. Guess what chapter 9 is? Where did that conversion factor come from? Not a chemical formula in black. From the chemical equation. That's chapter 9. Okay? That's it. Chapter 8 and 9. Done. Ta-da! So let's move to chapter 13. Okay? What we're trying to do is draw attention to that information and then take advantage of it and use it in some useful fashion. We can now convert substances. That's pretty cool. When we dealt with that previous example, milligrams to micrograms, milligrams was a measure of mass. Micrograms was a measure of mass. Well, that was pretty boring. I stayed in the exact same system. Now what can I do? I can change substances. I can go from one substance to another substance through that conversion factor. I have the power to do that. That's the power of the chemical formula. That's the power of the chemical equation. So those of you being like, wow, that's amazing. Have you ever made chocolate chip cookies?
Yeah.
Yeah, how'd you make them? Followed them through a recipe. You mean like a chemical equation? Yeah, that's exactly what it is. The chemical equation is your recipe. You just have to recognize the numbers that are associated with it and manipulate those numbers. Right? If you failed at making those cookies, it's probably because you didn't manipulate the numbers right off of the recipe. The same thing's going to happen here. Okay? Okay, so now let's push this a little bit further. What is the mass in grams of sodium hydrogen carbonate when 2 molecules of CO2 are consumed? Okay, and I'm going to argue that's actually more than I want. So let's take it back down to chapter 8, because that's now looking at a chemical equation. We changed a lot of stuff there. Okay. If I give you 2 grams of sodium, how many grams of sodium hydrogen carbonate are you going to make? Or sorry, sodium carbonate. We'll do hydrogen. What is that number? 2. Okay, I'm hearing a 2. It's a brave volunteer. I like it. Why are you saying 2?
I was thinking number of molecules, not grams.
So you were saying, well, Mike, you just wrote up that 2 atoms of sodium was equal to 1 molecule of sodium hydrogen carbonate, right? Whoops. We get a slightly different one, right? 1 and 1. Yeah, so don't the numbers just become the same? Okay. If I asked you to build a bicycle, how many wheels do you need? 2. What if I give you 500 grams of bicycle tires? How many bicycles can you build? Dude, you just told me you needed 2 wheels to build a bicycle. Why now all of a sudden you're like, oh, I don't know how to do that? They're different units. Is an atom the same thing as a gram? No, those are different systems. Grams is a measurement of mass. That conversion factor we built, not mass. It's looking at the number of those particles. It's looking at how many wheels went into that bicycle. Okay? So we need to come up with a way that we can find that information. To figure out how many bicycles I would need, what do you need to do to figure out from 500 grams of bicycle tires? How much does a bicycle tire weigh? Because then you could convert that weight into a tire that you can now build a bicycle with. Guess what you got to do for chemistry?
Same thing.
The exact same thing. So don't be jumping in and dropping 2s in there. The unit systems have changed. You can't do that. The chemical equation does not tell you a mass. Just like when you look at 2 bicycle tires, that doesn't mean it's 2 grams of bicycle tires. Right? Or even 2 tons of bicycle tires in a bicycle. Doesn't matter what unit you're changing that mass to, it's not going to add up. Okay? So when we look at that formula, we can break it down. Everyone's going to get sick and tired of bicycle tires. I apologize. Okay? I did not intend for that, but that was, unintended consequences. To build a wheel, we need spokes and a rim. So we could go through and build a formula for a bicycle tire, right? How many spokes are in there? Usually it's 32-ish. Okay, and a rim, right? God, that's a lot of stuff to write. I wish I had a shorthand that I could do for that. Like maybe say rims and S32. Oh, you mean kind of like a chemical formula? Yeah, exactly like that. That's the intent of our chemical formulas. It's to shorthand that work so that we can interpret what that information is. Okay? But it, again, does not have mass included in it. So we need to come up with some way to deal with that mass. Okay? Well, can you determine the mass of a rim? Yeah. Can you determine the mass of an atom?
Yes.
What balance are you going to use to determine the mass of an atom? That's not a balance, number 1. Okay? Or a mass. It's also not telling you the mass of the atom. What balance are we going to use? Like, to determine a mass, like I get a device and I put stuff on it and I weigh it. Okay? To get you an idea of scale, okay, the mass of atoms is somewhere on the order of, if we pick hydrogen, I'm probably going to screw it up, but that's okay. Actually, no, I remember it. Oof. I just forgot it. Damn it. Roughly the mass of hydrogen, ballpark, give or take a little bit. Okay. What is your balance measured to? You're in lab. The balance, what does it measure to?
Oh, like the limit of
001. Also known as 1 times 10 to the negative 3. We're only off by a little bit, just 21 units. Okay. To go to the next chemistry class, if you move into the next lab, the balances there report 0.0001. It's an extra $500 for that extra zero. Okay? And unfortunately, it's not a linear expression. It actually goes exponential. You add another zero, it adds like another $1,500. Okay? I need 21 more zeros. That's a really expensive balance. Am I going to be able to weigh a single atom? No. So my chemical formula that had that awesome power of saying, well, 2 atoms of sodium is 1 molecule of sodium hydrogen or sodium carbonate. That's a phenomenal conversion factor, but will I ever be able to deal with 2 atoms? No, I'd never even be able to weigh it. Okay? So how could I possibly do any science if I can't measure out these substances? Okay? I need to create a system where now when I run the reactions, I'm running at scale. Instead of running single atoms, I'm running thousands upon thousands of atoms. Okay, you might say, well, we would never do that in the real world. If you talk to a bicycle company, they're probably not talking about building 1 or 2 bicycles. They're talking about building thousands, if not hundreds of thousands of bicycles. Okay? Why do they not care about building 1 or 2 bicycles? They need to produce more so that they can satisfy demand, so that they can get money to live themselves. Okay? We need a much larger scale system. Okay? So when we scale up, we have to be able to come up with new unit systems to deal with this. Okay? That's the point of Avogadro's number. Okay? Avogadro isn't the one that discovered it. Okay? He was the one that presented, hey, we should come up with something like this, because if we don't have it, we're going to have a really hard time. Okay? So later on, we quantified it, and we then gave him credit for it or attached his name to it. Okay? And what we invented was a new term to represent this massive amount of molecules. And we called that a mole. Okay? And as you saw in the video, we've done this already. You've probably already experienced something like this. What have you experienced like this?
A dozen eggs.
You go to the store, are you really saying you're going to buy 12 eggs? No, you end up saying you're going to go to the store and buy a dozen eggs. Okay? What is that dozen?
12 eggs.
That dozen means 12. So when I say 1 times 12, I get 12 eggs. The dozen is a new number. I just invented a term for it to simplify my life. Okay? So in the video, we talk about why we would do this. Okay? Why do we invent new numbers or new units to represent these other numbers?
Let's make it easier.
How many of you can deal with 6.022 times 10 to the 23rd? Okay? That's kind of a big number. You can look at all sorts, like the video had you do weird calculations. There was that weird calculation at the end about money spent per day, all that, pennies, a mole of pennies. Okay? If you got the answer right, it came in at something like $14 million per hour for 100 years. Every person on the planet to spend that amount of pennies. That's a pretty big number. Okay? And that's every person per hour. That's a lot. Right? You can look at it, people do videos about donuts. If you took a mole of donuts, what would happen? Right? Or a mole of textbooks, what would happen? What would that fill? That number is so incomprehensibly large that our human brain can't deal with it. So what do? We get rid of it. We simplify it and call it a mole. Same thing's happening with a dozen. You're like, I can understand 12. No, you can't. That's why we invented the word a dozen. Okay? That is how pathetic our brains are. Okay? That's the point of this system. Okay? So what you now need to start doing is using it. Okay? Because once you start using it, eventually you can start to see the scale and the manipulation and why we would use it. Okay? And that brings in the value behind it, much like you're doing inches and centimeters. Okay? Or doing pounds and grams, or all those other kind of fun things. Okay, so take a swing at the question. How many oxygen atoms are in 0.240 moles of O2? I'm seeing a lot of calculators and it's bothering me. You should be doing some writing. And the very first thing you should be writing, what do you want to solve for? You should write that down first. Okay? So if we go through and try and set this up and solve. Okay? Where are we going to start? What do we want? So what do we want? Okay? I would argue that we should actually phrase it atoms of oxygen. Doesn't really matter. Atoms of oxygen, yeah?
Yep.
Does everybody agree with what I wrote there? Yeah, okay. What are we starting with?
Moles of O2.
Moles of O2. How many moles of O2 are we starting with?
0.240.
Okay. And then what was the next thing you wrote down? Okay, fair enough. Good point. Over 1. I can accept that. Okay, so really saying Avogadro's number, you should rein that back. Because Avogadro's number, already in the statement, I'm going to complain about it because it says number. I don't want a number. What do I want?
Conversion.
I want a conversion factor. In that conversion factor, what do I want?
1 mole, the denominator.
Moles of O2. Why?
Trying to cancel it out.
To cancel out what?
The moles of oxygen.
Okay, and what do I want in the numerator?
The conversion.
Okay. We could say atoms of what?
Oxygen.
Okay. So, number 1, the majority of people that I walked around and looked at did not write that. They wrote that. And I told them they were wrong. And I'd be like, but is that really going to change placement of my numbers? No, because it's still going to be 6.022 times 10 to the 23rd and 1 mole, right? What would I get for my answer? Numbers are lovely things. I get 14. 14 days and 2 weeks. Just so you know. What do you get? Okay, there we go. There's a better statement. We don't care about the number. We care about the units. What units would we end with? Atoms of oxygen, really? What does that 2 mean? There are 2 atoms, which means, am I looking at an atom of oxygen? What am I looking at? I'm looking at a molecule of oxygen. That's not atoms of oxygen. That's molecules of oxygen. Okay? When we look up at the conversion factor here, I know it says atoms, okay? And that's kind of sort of a misprint, but that's the standard that we typically reference. Really, that shouldn't say atoms. That should say things, okay? A measurement, or not a measurement, an object, okay? And when we look at chemistry, what are our things? Molecules and atoms. Are they the same thing? No, they're different. Okay? Those people say, well, you can't do that. A dozen means what? 12 what? You can't go into the donut shop and buy a dozen donuts? Can you buy a dozen bagels? Okay. We have to not just include the measurement, but also the substance. And we have to make sure that those things are tied appropriately. When we go through and look at this, this is intentionally a trick question. What were you asked to solve for? Oxygen atoms. And our symbol for oxygen atoms is O. What were we given? O2, which is an oxygen molecule. I can still get a mole of molecules because it's just a thing. It's just a larger thing. Okay? I can't get a mole of grams. Why not? What are grams? A measurement. Not a thing, but a measurement. Okay? When we're looking at Avogadro's number, it's the relationship between moles and things, whatever that thing may be. Okay? Just like a dozen.
So if you had that many grams of something, that wouldn't be a mole. It would be like just that many grams.
You wouldn't be able to tie those things as a conversion factor. You'd have to create a slightly different system behind it. And it ends up being a giant freaking mess that you don't want to touch. Okay? And that's ultimately because you're now referencing a gram as both the mass and the physical object of a gram. And that's why it becomes challenging. You're using the same word to describe two different things. Okay? So, how do we fix this? We do not multiply by 2. You're killing me. Oh, okay, thank you. I want molecules of oxygen in the denominator. Why? So the units cancel, and what do I want? I want oxygen atoms on top. What is the conversion factor between oxygen atoms and molecules of oxygen? 1, 2? This is why listing off numbers is a bad idea. Make sure you associate the unit with it. There are 2 atoms of oxygen in 1 molecule of O2. Now what happens? Molecules of O2 cancel. Moles of O2 cancel. Now you can punch it into the calculator. Make sense? Okay. This is a very subtle differentiation. You have to be very careful that when you now write out your measurements or your units, you're including the measurement and the substance. Why? We're doing chemistry now. In chemistry, those systems can change. We can be asked to convert substances. We can be asked to convert measurements. Chapter 2 was converting measurements. 8, 9, and so on, we're going to start introducing the concept of converting substances. Okay, so if you start leaving your substances off, you will get questions wrong. Okay? Subtle tweak. Make sense? Okay. Okay. One of the big things that kind of comes out of this is why did we pick 6.022 times 10 to the 23rd atoms? Okay, as the video was talking about, the whole point of it was to scale it up so that I could now actually measure these things on a balance. Okay, that's the point of a mole, is that I can now measure a large enough number of atoms that I can actually measure it. Okay? The number that we picked seems kind of random and arbitrary, but that number allows us to take the molar or take the atomic mass off the periodic table, and now instead of calling it an atomic mass, we can call it a molar mass. That's pretty insanely powerful. That's why we talk about Avogadro's number. So how often do we use Avogadro's number after that? Hardly at all. So I find it really silly when people get all excited about Avogadro's number. Okay, it's neat. Yes, it's cool. We can now make that a molar mass. Now I'm going to ignore Avogadro's number for the rest of my life. Yes, pretty much. Okay? Before Avogadro's number, what were the units on 69.72 for gallium? AMU. What is AMU? Atomic mass unit. Atomic because it's for a single atom. What's the mass unit? It's an arbitrary number to represent the number of protons and neutrons for the atom. It's just an invented mass system so that we can get those numbers. That was it. Okay, that's a pretty piss poor system. Okay, that's why we use Avogadro's number, because now those numbers underneath are no longer per atom. They're now for a mole. I can now measure each of those atoms out, okay, or those amounts out. And that's pretty cool. Now I can actually do science. Okay? So, what is the molar mass for copper 2 nitrate? Nitrite. Okay, how can we make this question more difficult? Let's try that first. It's really easy. It's really easy to make it more difficult. Where do we find molar mass? On the periodic table. What's represented on the periodic table? The symbols. If I just give you the name and you don't know any of the nomenclature or symbol meanings, you're screwed. It doesn't matter if you know how to calculate molar mass or do the addition of those numbers. If you can't find them, it doesn't work. Okay? So, what do we do? What is the molar mass for copper?
63.5.
How many coppers are in copper nitrite?
2.
Only one. So if we really wanted to push at this, we could start to do unit conversions on this. We don't have to. We can just say, well, if there's one there and there's one here, all I got to do is now say that mass is in that. What else is in that? Nitrogen. I heard a couple people say nitrite. That's cool. Nitrite is there. What's the mass of nitrite? I'd have to break it down into nitrogen and oxygen. So don't do nitrite. Do the mass of the elements. What's the mass of nitrogen? 14.01. Fine. How many nitrogens are there?
2.
How do you know that?
It's abbreviated right there.
We have to deal with those subscripts. Okay? You were all looking at me like, this is dumb to be looking at these stupid formulas. Dude, you'll screw it up if we don't talk about it. It's right there. We got to use it. How many nitrogens?
2.
2. Oxygen.
It's 16.
16. If we really got to be really careful, time 0.000.
And it'd be times 4.
Why times 4? I only see a 2.
Well, because there's 2 oxygen and nitrite.
Okay. We've got that parenthetical, so that multiplies out. Now what do we do? You add them all up. And guess what you have? The molar mass for copper 2 nitrite. You're like, well, that's boring. Why would I do that? You would do that because what we need to do is move into chapter 9 and now manipulate and use it. Okay? First, we got to trust that you can use it. Okay? Oh, look at that. That's a new question. What is the mass in grams of 0.532 moles of copper 2 nitrite? So let's just pause a second. Okay? Take a deep breath. New question. What do I want to do?
You want to find grams?
No, I do not want to find grams.
Grams of copper 2 nitrate.
I want to find the grams of copper 2 nitrite. Cool. Add that substance in there. What am I given to start with? moles of copper 2 nitrite, 0.532. Is moles the same thing as grams? No. So what am I going to have to do? A conversion. In that conversion, what do I want to have happen? Moles needs to cancel. Is that it? Just cancel moles? No. What else do I need? I need grams of copper nitrite. Okay, that's ideally what I want. Is that a conversion factor that exists? Well, maybe, I don't know. Good hedging. I like it. Okay. Yes. Where does it exist?
Not in my mind.
It's Avogadro. What is that called?
Where does it exist? I mean, grams per mole. Okay. So moles, and grams is a measure of mass. So I'm looking at a moles in mass. I'd be looking at the molar mass. It existed in the previous question. Ta-da! Where did we get that information from? Periodic table. So this conversion factor is there. You need to know where to find it. It's found in the periodic table. Okay. So what we would go through and do with our calculation is then have to go through and deal with all this fun stuff. 0.532. Now I got to write out all that work I wrote. Don't say I never did anything for you. Dang it, was it moles?
No, grams.
Grams.
Grams of copper 2 nitrate.
You gotta know what you need.
We want moles of the copper nitrite, grams of the copper.
So you put the molar mass on top?
Okay. So there's a good question. The number under copper is what? 63.55. 63.55. Not quite. We can run with AMUs. AMUs is a measure of mass. So 63.55 is associated with mass. Okay? To your gram question, it does not say 63.55 grams. It says 63.55 grams per mole. It's a molar mass. Okay? If I take 6.022 times 10 to the 23rd atoms of copper and I add up all of the mass of all of those coppers, guess what I get? 63.55. So that is the number of grams for 1 mole. 63.55 grams per mole. Whoops, just for the copper, because I didn't do it for the other one. That 63.55 is closest to which unit? Grams. The number that you calculated from that previous question, anybody get it? Needs to go with the grams. Not on top, not on the bottom, with grams. Moles underneath. Now what happens? Moles cancel and I'd be left with grams of copper nitrite. And that is what I'm looking for, which means I can now punch it into the calculator and I've got my answer. Wait. What do you got? Yeah. No. You got angry. You should be happy that you got angry. Yeah!
So the 155.57.
Where did that come from?
That's just all of the masses.
Yes.
Okay.
Yep. The 155.57 is the mass of copper. The mass of how many nitrogens? 2. The mass of 4 oxygens. You add all that up, and I'm just trusting you all that we got 155.57.
And then 82.8 grams of
Okay?
copper.
And because everybody seems to like numbers, let's go ahead and pull that out. The number we get is 6 grams. Okay, would that be a correct answer? No.
I'll take the copper 2 nitrate.
Okay, I would have to include the copper 2 nitrite which I'm kind of saying is above it. I know, I'm being lazy. But it's still wrong. Sig figs. You were given 3 sig figs, which means the answer needs to be reported to 3 sig figs. That first insignificant digit is larger than 5, so I need to add 1, and our number becomes 82.8 grams copper nitrate.
Okay, so this is multi-mass conversion. So the one we learned previously, the last question we just did, what is that?
What did we convert? Oh, because I just got rid of it.
Not like,
Where is it? What did that one convert? I remember, shouldn't say atoms, it should say things. Okay? And I know you're like, oh, that's stupid. I don't even know what that means. What is 1 dozen? 12 things. Okay? It's the exact same concept. Okay? And just for those people like, oh, haha, it's so easy. I wouldn't quite go that far. Okay? It's a little bit hard to deal with and trick out and play with. Okay? It's easy to mismatch it. This is why you need to write out the units. Okay?
we still, okay, we're not there yet, but
Did we have to use Avogadro's number in that previous calculation?
no.
No. It's completely unnecessary.
But then are we going to get like converting moles to other things?
Could I ask you to convert moles to other things? Hell yeah. Okay? I could make you convert moles to liters, moles to milliliters, moles to grams, okay? Moles to atoms, moles of one substance to the moles of another substance.
Oh, you need moles to moles.
Okay? We can get moles going every which direction. Okay? So, what is the mass in grams of 2.55 times 10 to the 23rd atoms of lead? Okay, so I heard a so weight, so we'll run it this way. With the so weight, are we working through this together or are you doing it individually? Want an individual? We'll get an individual, okay.
But I'm just checking, this is still a multi-mass problem?
So, before we start jumping out and over-classifying these as mole to mass and all that, the problem that I have with the way the textbook represents these is, mole to mass or mole to mole, okay, is it starts building in this formulaic aspect. It's dicey territory to be in, and I know you want to go there. This is why I told you the conversion process. Okay? I don't want you in that category because that means what you're getting out of this class is now the ability to convert moles to mass. How many of you plan on being chemists? How many of you plan on doing anything that would ever require a conversion? Okay, you need a conversion process, not a mole-to-mole process. Okay? So I don't want you getting over-reliant in this is how I convert moles to moles, or grams to moles, or mass to moles. What you need to do is focus on what are you being asked to convert. Let's move through with what we've got. Okay? At very least for nursing, I can explain, or I can at least point to this. There is a test in the nursing program where all you do is convert. If you fail that test, they throw you out of the program. Not like, I get to go back. No, you're out of the program, and you have to go through the whole application process again. Okay? Kind of a big deal. Okay? Why would conversions be a big deal? What are they doing with that conversion test in nursing? Medicine. Converting micrograms per kilogram for the patient. You would have to know about how much medicine that you're supposed to be giving a patient, because if you screw it up, you could kill the patient. So they take it pretty seriously. Okay? What I'm setting you up with is the skill to be able to do those conversions. Okay? Without killing somebody, hopefully. Okay, so to lead you in it, I'll guide both ways because we had a request for individual and a request for together. Step 1. What do I want? Grams of lead. What am I starting with? 10 to the 23rd. Ideally, what happens?
You want to for
Atoms of lead disappears, and I would want
grams.
grams of lead to appear. Does that conversion exist?
No.
No. Which means you get to decide now which one you're going to deal with. Now you can carry on. And if you got questions, just raise your hand. Either one works, believe it or not. Okay. Interestingly enough, the way I've got this written sets up and matches pretty closely the way a lot of people wrote this. What I'm asking you to do is to include a measurement and the substance each time, which means you're going to end up taking up a lot of real estate on your page. Okay? I still think that you should be doing it. That real estate is valuable enough that you should be consuming it in through your solve. So if we set this up, the way I saw a lot of people going was atoms of lead, and we want to convert that into moles of lead. Why did we pick moles of lead and not grams of lead?
You know the conversion.
We don't know the conversion to grams of lead in comparison to atoms of lead. Do I know a conversion between atoms of lead and anything else? I do know it to moles. Okay? That conversion is Avogadro's number, which was
6.022 times 10 to the 23rd.
okay. 6.022 times 10 to the 23rd.
No.
Okay, no. When you string out a number, I'm going to place it wherever the hell I want. Okay? You need to tell me where to place that number. It goes with atoms of lead. Wow, that's even a better response instead of being, it goes on the bottom, you idiot. You're right, it goes with the atoms. Exactly right. Okay? It doesn't go on the bottom or the top. It goes with the atoms. Because the atoms are placed in the bottom, that is why my number will be tied to that. Why is it atoms? Atoms are a thing. So I can put that there. Okay? When we write moles of lead, we're actually doing an abbreviation. This isn't moles of lead. You're like, damn it, I just started getting this figured out. Why are you changing it on me? What is it if it's not moles of lead?
Moles of the thing.
It's moles of atoms of lead. Okay? That atom of lead is implied in this system. Okay? We just decided not to include it. Why? Because I didn't want to write atoms again. Okay? But it is already embedded within that. And it's not going to change any of our calculation. Okay? And we place the 1 there. You'll notice that in this calculation, do I have any space to insert another conversion?
No.
No. So here's where 2 things potentially happen. Okay? Number 1, someone will go through and say, well, I'm not going to solve for grams of lead anymore. I'm going to solve for the moles of atoms of lead. And because some of you were like, oh, that atoms must be wrong. I'm going to prove you it's not. Okay? That's okay. The issue with that is you're now going to get a number that you're going to put here. Okay? With that number, you're probably going to be lazy, and you're going to start to round. Do you still have to do another calculation? Yeah. Which means when you do that next calculation, it's going to give you a new answer that is wrong by however much you've rounded. Which means you may not get an answer in your multiple choice. Does that make sense? Okay. As long as you're aware of that, cool, do whatever you got to do. Okay. That is one of the reasons why, instead of switching out what this equals, I would leave it as grams of lead. Whoops. But then just say, and of course this looks ugly,
Do an arrow.
doing a new line underneath. And in that new line, what do I want to have happen?
You want to get grams on top of it.
I want grams of lead, and in particular grams of what kind of lead?
Atoms.
Atoms of lead. And I want on the bottom
Moles of atoms of lead.
don't lose your mind yet. Give me a break. Where do I find that conversion factor? That's on the periodic table. Make sure you look up the correct element. In this case, where to go? PB 207.2 grams, because it's a mass
Of atoms of lead.
of atoms of lead per 1 mole of atoms of lead. The atoms of lead cancel. We don't have to worry about it. Okay? Now I can enter it into the calculator and I get my final answer.
87.7.
Grams of lead. Okay.
87.8.
Grams of atoms of lead.
Isn't that the same thing as we had last time? Was it?
Close.
It's close. It was very close. Okay. 87.8 grams of lead. So if I take that large amount of lead, I can actually get a mass I can measure. That's the point of a mole. It's scaling up the amount of atoms to a point where I can now measure it in a lab. That's the point of this. Yes?
So how did they figure out how much number? Like, how was that derived?
It constantly changes, believe it or not. Where one of the reasons it was derived is defining carbon, the pure isotope of carbon at carbon 12, and then looking at the mass of a mole of carbon 12 atoms and defining that to be 12.
How do they know it was a mole?
They define it to be that.
Okay.
Yeah, so it's a definition.
Like it does.
What is the mass in grams of a single molecule of sulfur dioxide? What are we solving for? Okay, you'll notice that I will write MLC for molecule. Why would I not write MOL? Because that's a mole. I'm trying to delineate. A mole is not a molecule. Those are two different things. Okay, so MLC what? Sulfur dioxide. What am I given? I'm given molar mass. Okay. 64.07.
Grams of sulfur dioxide.
Should I have placed it that way? Why?
We're looking for mass and we're starting out.
I'm looking for mass in the numerator. I'm starting with mass in the numerator. Okay, so cool. I brought in the mass of sulfur dioxide. Fantastic. Okay, you'll notice I didn't write MLC next to that one. Do I need to write MLC? Why not? SO2? How many elements is that?
2. 1.
2. How many atoms? 3. If I collect 3 atoms, what do I have? A molecule. Do I need to say the word molecule? No. Right? I have moles of SO2. Do I want moles of SO2? So what needs to happen? What do I want to convert moles of SO2 to? Or actually, am I given moles of SO2 in the question? Okay, with grams, so that's a very fair point. I could do grams of SO2. What does that do to my previous calculation? It cancels it out. So that was there, but that's not going to be very useful. Am I given moles of SO2 somewhere else in the question?
You're only, what is the mass of the You're only given
What are you saying I'm given? I'm given a single molecule. Am I given anything about the moles?
No.
No, what am I given again? A single molecule, whoops, that's an eraser. A single molecule, also known as one molecule of SO2.
So
I need to incorporate that information into this question. How do I cancel out the moles? Molar mass is already there. I'm going to use Avogadro's number. What are you going to convert moles to? Why do you want to do molecules? We're doing molecules because we're given molecules. For those of you saying atoms, we aren't given an atom of SO2. We're given a molecule of SO2. What is the conversion factor between moles and molecules? 1 mole is? 23rd molecules. What happens to the mole unit? Moles SO2. I would now have the grams per molecule of SO2. How many molecules of SO2 am I being asked for? 1. If we look at my answer, it just says grams of SO2. How do I get rid of the molecules of SO2? Molecules of SO2. How many molecules of SO2 was I given? 1. Ta-da! I've already got grams. That is the molar mass. I started with the molar mass. Okay? So what we're stringing together is a sequence of units. Those units are new and foreign to you. Okay? With practice, you'll start to get used to what the meaning of those units are. You gotta start the practice. We'll pick up there